Hello guys, good morning. Today we will be discussing the analysis of stress in a continuum. And before we proceed, let me first give you some definitions on the terms and notations we are going to use here in this presentation. So let us define first what is a continuum, or what is popularly known as a continuous body. So a continuum is simply a body, which is made up of a material assumed to be totally continuous. It means there are no gaps or any empty space in between them. Hence, the molecular structure is disregarded. So for the properties of a continuum, let's define two important properties we will be considering in our computations when we discuss the analysis of stress and deformation. So the density is defined as the limit of the ratio of your differential mass. Okay, so this is the differential mass with that of the differential volume as your differential volume delta V approaches 0, and you normally designate density as uh, the raw variable. So for the temperature T, we define it in a different manner, aside from knowing that it is simply a measure of how hot and cold a body is. So we look into temperature as a function of the variables that defines your position in space, x1, x2, and x3, and of course the time t, which is normally a variable of concern for which the temperature is may be referred to initially and at any time lapse t. So it is then the mean value of the kinetic energy of the random motion of the molecules in a volume surrounding a certain point P when it is in the thermal, chemical, and mechanical equilibrium with its surroundings. So holistically, temperature uh, is defined technically in this manner. And for the classifications of a continuous body or a continuum, we have normally two types. Okay, we have the fluids, which involves, of course, the liquid and the gaseous type, and the solids, to which most structural materials are made of. So the difference between the two is that your fluids describes your continuum in terms of its flowability, or in terms of how the body flows upon the action of an applied force, while solids uh, are defined in terms of a continuous body which deforms upon the action of an applied force. So for the forces, let me underline the these two important distinction between the motion involved in a fluid body and a solid body. So flow and deformation are the two descriptions that differentiates fluids with solids. For the forces, we have basically two force type that we will be encountering. First one are called the body force, which are of course the forces that are not in direct contact with the body, and it is normally described in terms of its gravity and mass or inertia. Okay, so we normally use the variable Fi or Yfi to define the body force in terms of a force per unit mass and a force per unit volume. Okay? So for the surface force or the traction force, these are the forces due to direct contact with the body, such as the live loads that acts on a structure like wind, flood, and earth loads. So for the components of the stress tensor, we now derive a basic formula on how the stress tensors are converted into what you call traction forces. Okay, so from a tensor, we convert it into a vector sigma. So the order or degree of the quantity here for tensors are of course on the second order, upon which if we convert it to a stress vector or a traction vector, so normally is termed as traction vector in other references. So we are now converting a second order tensor into a first order tensor, which is a vector. So if we consider now stress vector sigma I acting at an arbitrary sloping surface dAI, normal to Ni, then we determine the components of the stress tensor sigma ij in this regard. Let's look into this figure. If we have here a set of Cartesian coordinate axis in a right-handed coordinate system. Okay, so this is y1, y2, y3. So the permutation is actually on a counterclockwise order. Okay, so this is now a right-handed coordinate system upon which your orientation is observed on the positive octant of the three-dimensional axis. We now consider a traction vector or stress vector, sigma I, upon which the orientation is reckoned from a normal vector Ni. When you say normal, the angle upon which this direction is reckoned from is 90 degrees from the this surface described by this tetrahedron. Okay, so your point of reference is actually a point Q measured from the origin P at the distance h. Okay, so if we take a look now on the traction force and observe what happens at this particular point, we can now describe. Okay, so a quantity of interest in terms of a tensorial uh, quantity at this point. So if I make use of a representation of this point based on a cubical element which are infinitesimal in nature. Okay, so I have now here a cube at this point, so I may describe my tensor in terms of the sigmas, considering a positive value as referred to the right-handed coordinate axis. Okay, so if I now make use of such, so my sigma 1 1 will be referred to a positive direction on 1. So this is a sigma 1 1, and this will have a positive direction on y2, which is sigma 2 2, and a positive direction on y3, which is sigma 3 3. So these three forces now are called normal forces, okay, upon which your cubical element is expected to deform in terms of contraction, compression, or tension. So these are now the normal forces, while if we take a look at the shear forces, no, the shear forces are actually directed on the face. Okay, okay. So if we consider now this as your uh, uh, face uh, 2. Okay, so this is your face 2. This cubical face is actually on the side of your is perpendicular to your direction y2. So this is now a sigma, a shear stress on face 2 directed on axis 1. So you now make use of a sigma to 1 here. Okay, and while this vertical becomes now a sigma on face 2 directed on direction 3. Okay, so that's how shear stresses are described in terms of index or subscript. Okay, so this is now a phase 3. So this is now your sigma. Okay, a sigma on phase 3 directed on axis 1. And you have also here a sigma on phase 3 directed on axis 2. Okay, so let's try to make our representation much more uh, clear. Let's okay, draw the cubical element figure. Okay, so this is now your representation on the sides of the first octant. Okay, so this is now a phase 3, phase 1, and phase 2. Taking note that okay, our shear are actually the tangential stresses on the face of on the surface of whatever is represented by the face, no? In that perpendicular to that direction. So this is your face one. So we have here a shear directed on one and a shear directed on three. Okay, so we can erase this. Okay, so this is now a sigma 2, 1, and this is a sigma 2, 3. While here we have a sigma 1, 2, and a sigma 1, 3. Okay, and here we have a sigma 3, 1, and a sigma 3, 2. So for the normal stresses, we therefore make use of the perpendicular, okay, directions. So this is now a sigma phase 2 directed on 2. This is a sigma 1 directed on 1, and this is a sigma 3 directed on 3. So all in all, we have 3 normal forces and 6 shear stresses defined in terms of your sigma ij's here. Okay, so this is now your sigma ij. So if we take a look at the matrix of sigma, or what you call the stress tensor, I have now here a sigma 1, 1, a sigma 2, 2, and a sigma 3, 3. Okay, so, and this is a sigma 1, 2, sigma 1, 3, sigma 2, 3, which is also equivalent to sigma 2, 1 there, sigma 3, 1, and a sigma 3, 2. Okay, so the diagonal elements are therefore considered as your normal stresses. And your off-diagonal elements are considered your shear stresses. Okay, so these off-diagonal elements are considered your shear stresses. Okay, so the I del refers to the axis upon which the normal direction is perpendicular to, or the surface rather, upon which the normal direction is perpendicular to, while the J is the component of the stress tensor upon which the direction, okay, so your J, so if I have a sigma I J, so your I is the normal to the n vector. Okay, so this is the surface normal to the n vector, while J is the direction upon which your stress is referred according to the coordinate system, in this case the right-handed coordinate system. Okay, so if we define now a force, we know that a force is simply equal to the stress multiplied by the area. So this is now a stress vector. So the stress vector multiplied by the area is equal to the force. And if you expand this, I may now get it. Now if I know the values of each and every uh, quantity inside this array or matrix, then I can compute simply for the force vector or the traction vector. So we call this now a, a stress vector or the traction vector F1, F2, F3. Given by this formula, upon expansion will lead to this one here. And using equilibrium equation as derived, okay, as derived uh, we now get, okay, the body force plus the traction force is equal to the resultant force. Okay, so this is the body force. So the body forces, which is brought about by the weight or the gravity upon which the density is being referred to in this case, will be contributory to the body force. So this, since we are on static equilibrium, we don't care about the inertia force yet. No? But when we go to dynamics, okay, this body force will involve additional inertia force, okay, in dynamics. So if we go to structural dynamics later, then this will be increase in terms of the inertia force as described. No? Not necessarily increase, but there will be an additional consideration of an inertia force or the reverse effective force or the D'Alembert's force that will create some change in the dynamic equilibrium of the system that we are solving. Okay, so by changing or substituting your Fi defined here with Nj sigma Ji A, okay, so I just change now the subscript since I interchange uh, my okay, my subscript Jij here to Ji, I have to place your Nj in front, okay? So this becomes Nj sigma Ji dot A, okay? So this is a transposition brought about by the matrix transpose of sigma Ij to sigma Ji. Okay, so when I multiply a matrix with a vector, okay, so this is a matrix with a vector, and then I change it the direction, I must get the transpose of that vector, okay, then multiply it to the transpose of the matrix, okay. That's why here your Ni became Nj, okay, and your sigma Ij became sigma Ji. So take note that the differential volume will approach zero as h approaches zero here. So if we are considering a very small infinitesimal cubical element, so this is a very, very small element, then your h distance here from P to Q will actually be approaching zero. Hence, the differential volume of this tetrahedron as referred to this figure will now vanish, okay, by simply putting this into zero. Hence, what will remain is a sigma I multiplied by A and nj sigma ji cancelling both A's here. I have now my stress vector formula in terms of sigma I is equal to sigma ij ni, or can transpose it into a sigma i's nj sigma ji. Or in terms of vectorial operations or matrix operation, this is simply vector sigma is equal to the normal vector and multiplied by the stress matrix sigma. Okay, so you call this now the formula for a traction vector or a stress vector. Okay, so this stress vector now is solved by simply making use of the stress tensor multiplied by the normal vector. And in matrix multiplication, it's easy to come up with an n dot sigma for this particular case where sigma n and sigma here are the stress vector, the unit vector, normal vector, the stress tensors, respectively. Okay, so that's it for the first part of our introduction with the analysis of stress. I hope you have understood what the terms and the notations are all about, the definitions of the properties involved, and also the derivation on how the stress vector or the traction vector came up by the description of the, the, the stress tensor given and the normal vector as uh, represented or presented here in this figure. So I'll see you in the next video, and thank you for listening.